Welcome to this lecture on chemical curiosities. I'm going to start with the liquid in this container, and I'll just pour some into this cylinder. So you can see it's a nice bright red colour. But let's see what happens if I keep pouring. Well, I think you can see every time I pour out the liquid, I seem to get a different colour. So, in the dictionary, the word curious is defined to mean something which is puzzling or surprising or unexpected. And this demonstration might seem rather puzzling at first until we realised that the cylinders were not empty at the start. Each of them had a little speck of chemical which reacted with the liquid in this container, and it produced a colour change. We'll look at the chemistry of that in just a moment. Let's have a look at the liquid in these two beakers. They're both colourless. But let's see what happens when I pour the liquid from this beaker into this one. So, again, we see a colour change. It's turning blue. The blue is getting darker. But as I keep pouring, it goes away again. That's also rather odd. It seems as if a chemical reaction began and produced a colour change, and then it sort of changed its mind and went backwards. So did it go backwards? Did that chemical reaction go backwards? So the chemistry of these demonstrations is based on a simple idea, which is that every substance can be thought of as either an acid or an alkali. And if it's neither, if it's sort of in the middle, we say that it's neutral. Now, we can use certain substances to tell us whether a material is acid or alkali, and probably one of the most famous of these is called litmus. So litmus is a material which is red in acid conditions and it's blue in alkali conditions. But there are lots of other indicators, and the one we used in this experiment was called universal indicator. So this has a range of different colours. It's red when things are strongly acidic. In the middle, where things are neutral, it's green, and in strongly alkali conditions, it's purple. And this experiment was based on an indicator called phenolphthalein, which is colourless in acid and it's blue in alkali conditions. So these cylinders had different amounts of acid and alkali in them, producing the various different colours. In this experiment, the first beaker had a mixture of phenolphthalein and some acid, and the second beaker had some alkali. And the key to this is that when acid mixes with alkali, they react to produce a salt plus water. So they're sort of opposites, they kind of cancel each other out. So as I started to pour the liquid, the acid and phenolphthalein from here went into the alkali, but the alkali quickly cancelled out the acid, so the phenolphthalein is now an alkaline solution and it turns blue. But as I keep on pouring, I'm adding more and more acid, it's neutralising the alkali, and eventually this beaker becomes acid as well, and the phenolphthalein goes back to being colourless. So this reaction was not going backwards, it was just the same reaction all along. Well, we could ask, is there a chemical reaction that goes backwards? Can chemical reactions go backwards at all? Well, that turns out to be a really interesting question, and it's a question that we're going to come back to several times during the course of this lecture. But let me just show you now another example of a reaction involving universal indicator, and it's this column of water which has universal indicator and also a little bit of sodium hydroxide, which is alkaline, and so it's turned it this sort of bluey purple colour. And we're going to add some acid, and we should see it go through a sequence of colours rather like these. Now the particular acid that I'm going to use is acid that's going to be made in the water from carbon dioxide. So in this beaker I have carbon dioxide, but it's frozen. It's at minus 79 degrees centigrade and it's become a solid. We call this dry ice, because when it warms up it doesn't melt to a liquid, it goes straight to a gas, so it's always dry. So when I add the dry ice to the water, it will react with the water to form an acid called carbonic acid. That's the same stuff that's in fizzy drinks. That's what gives the fizzy drinks their fizz. So let's see what happens when I add this. Now watch for the colour changes. You should see that sequence of different colours. Okay. So in all the reactions we've seen so far, we mixed two things together. It produced a chemical reaction which gave rise to a colour change. So let's have a look at this flask. This flask has a colourless liquid in, but if I shake the flask, it turns blue. That's a bit surprising because I didn't seem to be mixing two things together. I was just shaking up a single liquid. Here's another flask. It's a similar idea. This is a yellow liquid. If I shake it, it turns red. And if I gave it a really good shake, it turns green. Now, something else rather surprising about this as well. If we keep watching, the green is turning back to red. And if we look here, the blue is turning back to being colourless. And in fact, the red will go back to being yellow. So it's going back through that sequence of colours again. And what's more, I can even repeat it. So if I shake it again, it goes back to being blue. If I shake this again, it goes back to being red, and so on. And if I wait, it will go back. So again, it looks as if we have a chemical reaction that's going backwards. But the first mystery is, why do we have a colour change at all? I didn't seem to be mixing two things together. What we have to remember, of course, is that this flask not only contains water, but it contains a gas. In fact, the gas is just air. And air, of course, is a chemical. And when I shake the flask, I'm mixing oxygen from the air with the liquid, and that's producing the chemical reaction. So the next question is, did this chemical reaction then go backwards as it fades from blue to colourless? Is it a chemical reaction that's going backwards? Well, unfortunately, it isn't, because what's happening is there's a second chemical reaction taking place. This flask contains a dye called methylene blue, and when it reacts with oxygen, it goes from colourless to blue, but also in the flask is some glucose, and that glucose slowly turns the methylene blue from blue colour back to being colourless. And this is the same idea, but with a different material called indigo carmine. So again, we didn't have a chemical reaction going backwards, but we're going to keep on looking for such a reaction as we go through the lecture. So in the reactions we've seen so far then, we mix two things together and we got a colour change. So let's have a look at what happens when I mix these two colourless liquids together. So first of all, this machine is just called a magnetic stirrer. It just spins this little magnet and keeps the liquid stirring. It's just because I'm too lazy to stand here and stir them by hand. So we have a colourless liquid being stirred, and we add a second colourless liquid, and watch closely and see if you can detect a colour change. So keep watching. Okay. Very strange indeed. We mixed the two chemicals and it seemed as if no reaction took place. It just sat there for 10 seconds and then suddenly it reacted. Now that seems very odd, very surprising. But what was really going on? What was really going on is that there were actually two different chemical reactions taking place inside this beaker. The first reaction was quite a slow reaction. It was a reaction between two chemicals that produced iodine. So you imagine this reaction taking place and slowly releasing iodine into the solution. Now the iodine would appear as a sort of brown colour. You can't see the iodine because there's a second chemical reaction taking place. There's a material in the solution which is reacting very quickly with the iodine, and it's absorbing the iodine as soon as it's produced. And the secret to this is to arrange that that second material is in short supply. So the iodine is being produced slowly, it's being mopped up by this second material as soon as it's produced, but when that second material runs out after about 10 seconds or so, the next little piece of iodine to be produced remains in solution. And because the iodine's a bit hard to see from the back of the room, we've added some starch. The iodine reacts with the starch and produces a very dark blue colour that appears to be almost black. Okay, so that's called a clock reaction. So now that you understand how that one works, have a look at this one. So this involves three colourless solutions. So I pour that one into there, and I pour this into here. Again, watch closely. Okay, so that's a sort of two-stage clock. So I'll leave you to think about how that one might be working. So in the reactions we've seen so far then, we mix chemicals together and we know that a reaction has taken place because we get a change of colour. But there are lots of other ways that a chemical reaction can show up. And one way is called a change of state. So the state of something just means whether it's a solid or liquid or a gas. So if something turns from a solid to a liquid or from a gas to a solid, then it's changed state. So let me show you an example of a chemical reaction that involves a change of state. So I'm going to use these two liquids. I have a red liquid and a colourless liquid. What I'm going to do is to pour the colourless liquid onto the red liquid very carefully and try to make two layers. So what I want to happen is for the colourless liquid to be floating on top of the red liquid in separate layers so that they don't mix. Okay, so I think that's worked quite well. So what I've got now is one liquid floating on top of another, and where they meet, they undergo a chemical reaction. And they're actually making a solid. A solid material is formed where the two liquids meet. And what I can do is to fetch out some of this solid material. And as I pull it out of the beaker, of course, it allows the two liquids to meet each other again, and so they react again to form more of this solid. So if I'm careful, so as I wind, I'm pulling up this material and it allows the two liquids to meet again and it forms more of this material. And this substance that's being formed is actually nylon. So we're making nylon as I speak. And if I'm careful, I'd be able to just keep on turning this and making this long thread of nylon, at least until we run out of solutions. Okay, so that's an example then of a chemical reaction that involves a change of state. So let's have a look at another reaction that involves a change of state. And for this, I'd like a volunteer, please. Who would like to volunteer? You're very keen. Come on down. Let's have a big hand for a volunteer. You would like to stand there. Just pop those on. What's your name?
Dylan.
Dylan. All right, Dylan, if you stand just there, we're going to do some chemistry and we're going to make it a solid. All right, I'm going to start off with a flask that contains a solution of silver nitrate, and I'm going to add a little bit of ammonia. Now when I add the ammonia, you see that it's forming a sort of brown colour. I'm going to keep on adding the ammonia, and in a minute that brown colour should disappear. There we are, it's disappeared, isn't it? Now what I'm going to do is to add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So I'm now going to add more ammonia. And again I'm going to add ammonia until the liquid goes back to being colourless. This takes a moment or two. There we go. And then finally I'm going to add some glucose. So there's the glucose. Now I'm going to put the lid on, put a clip on. I'm going to give it to you, Dylan, and I want you to hold that, and I want you to give it a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place, and it's forming a solid. And the actual material that it's forming is silver. We're making pure silver metal. Keep shaking. It takes about 3/4 of an hour. Is that okay? It does actually take a minute or two, but the harder you shake, the better it works. So keep shaking. Don't drop it, though. Okay. So metal, silver metal, is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, we should see silver metal in the form of a mirror building up on the inside of the flask. And you'll all have seen those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. The little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, let's just have a quick look. Almost there. Keep going a little bit longer. Still looking a little bit dark. Excellent. All right, give it back to me then. Right, I'm going to take the clip off. Take out the stopper, just wash that off. And I'm going to pour out the remaining chemicals. And then I'm going to rinse this out with distilled water. I'm going to rinse it out a second time. Rinse it out a third time. There we go. And I'm just going to put that on, just dry this off. And put the clip back on. And if you'd like to just give that a little polish. There we go. If you'd like to hold it up by the neck, that's it. And if we bring a camera in and have a look at this, and we've got a lovely silver mirror. There we go. Just stand there. Okay, what I'm going to do is give that to you as a souvenir to take home, and you can go back to your seat. Let's have a hand for our volunteer. Okay, so that's an example of a chemical reaction that produces a change of state. I want to show you another example of a chemical reaction. Again, this is going to go from being a liquid to being a solid. So in this flask I have a solution of sodium acetate, and this sodium acetate's a liquid, as you can see, but it would very much like to be a solid. It would like to turn into a crystal. But it needs a sort of an excuse to get going. And the excuse is going to be some little crystals of solid sodium acetate in this dish. So watch what happens as I pour the liquid onto the crystals. So I think you can see there the liquid, as soon as it touches the crystals, is turning into a solid. And with a bit of luck, we can make a sort of chemical sculpture. Seems to be working. Okay, so that's a sort of sodium acetate sculpture. Now, oddly enough, this actually has a practical application, and this is the practical application. This is something called a hand warmer, and it's a plastic pouch, and it contains exactly the same liquid as in this flask. It's a solution of sodium acetate, and it would like to turn into a solid, would like to turn into a crystal, but it needs an excuse to get going. And the excuse is this little metal disc, and if I just flip this disc backwards and forwards, that should be enough just to start the crystallization off, and there it is. And we can see the liquid turning into a solid. And as it does so, it's actually getting warm. So it's actually giving off heat. And there it is, it's turned entirely into crystals. It's become quite warm in the process. I can put that inside my glove and keep my hands warm for half an hour or so. And then I can take this and put it into boiling water for a couple of minutes. The crystals will turn back into a liquid. I can allow it to cool, and they'll stay as a liquid, and it'll stay like that for weeks or months until I'm ready to use it again. I can use it thousands of times. Okay, so that's sodium acetate, a sort of chemical sculpture. I'm going to show you now another way to make a chemical sculpture. And Chris has been preparing this. This beaker contains a mixture of para-nitroacetanilide and sulfuric acid. And Chris has been warming it up. And when it's hot enough, it will undergo a reaction in which this liquid will turn into a solid. This makes quite a bit of smoke, so we've got this special hood that will suck away the smoke from the reaction. Okay, here it goes. All right. Okay, so that's a chemical reaction that involves a change of state. So we've seen lots of chemical reactions now in this lecture. We've seen reactions that produced colour changes. We've seen reactions that produce changes of state. And we're asking ourselves the question, could a chemical reaction go backwards? Now, we've seen several reactions that appear to be going backwards, but when we understood them a bit more carefully, we realised, no, they weren't going backwards. So we'd still like to understand whether a chemical reaction could ever go backwards. Now, to do that, we first of all have to ask, why does a chemical reaction happen at all? Why do chemical reactions happen in the first place? Well, to understand that, we're going to look at some very simple chemistry, and it's the combustion of hydrogen. So Chris has filled a balloon with hydrogen gas, and we're going to set fire to the balloon. And what will happen is the hydrogen will react with the oxygen in the air, and that will produce a small quantity of water vapour, and it will also release some energy. Okay, so this is the reaction of hydrogen with the oxygen from the air. Here we go. Okay, so can we just have a show of hands? Can you put your hand up if you enjoyed that demonstration? Oh, that's quite a few. Can you put your hand up if you'd like to see a slightly bigger one? Okay, that's everybody. All right, come on then, Chris. Okay, now the last balloon made quite a pop. This one is going to make an even louder pop, quite a loud bang in fact. I'm standing quite close to this, so I'm going to be wearing ear defenders. What you might like to do is to cover your ears for this one, because it could be fairly loud. Okay, and we'll bring down the lights. This is the reaction of hydrogen with oxygen. So I think you'll have noticed in that reaction that energy was released. Clearly. So we got a lot of noise, we saw the flame, we saw the light, I could feel the heat, and probably you in the front row could as well. So energy was released in that reaction. So what was happening is that the starting material, the hydrogen and oxygen, were in a sort of state of high energy. And as a result of the reaction, they moved to a state of low energy. Now, the total energy in the world is always conserved. You can't create or destroy energy. So that difference in energy was given out. It was given out in the form of that bang, the heat and the light and the sound and so on. So maybe that's why chemical reactions happen. Maybe chemical reactions happen because the chemicals move from a state of high energy to a state of low energy, and they give out that difference of energy. So it's a bit like taking a ball and putting it on a slope. If you put a ball on a slope, it rolls downhill. It goes from a state of high energy to a state of low energy. So maybe that's how chemical reactions work. If it is how chemical reactions work, then it's pretty obvious that a chemical reaction could never go backwards, because going backwards would be like putting a ball on a hill and having it decide to roll uphill. And that's not going to happen. Okay, so we'll keep that thought in mind, and we'll look at some other examples of chemical reactions that give out energy. Now, we've seen energy being given out in the form of a bang. We saw a little bit of light being given off there in the form of that flame. I now want to show you a reaction that gives off a great deal of light. And it's the reaction of a rather special element. It's called phosphorus. And the word phosphorus comes from the Greek. It means the giver or the bearer of light. So this is a reaction that will give out a great deal of light. So we could just burn a little bit of phosphorus on the bench, but we thought we'd do is to scale this up and do this on the largest scale we could. And so this is actually the largest flask that you can buy in the UK. And so this is about as big as we can make it. And we're going to burn quite a big chunk of white phosphorus inside this flask. And to make it burn really well, we're going to fill the flask with pure oxygen. Now, in order to fill the flask with pure oxygen, we're going to use liquid oxygen, and we're going to make the liquid oxygen by starting from another liquefied gas, liquid hydrogen. So in this vacuum flask, I have some liquid hydrogen. It's a colourless liquid. It looks pretty much like water, but it's at a very low temperature. It's at minus 196 degrees centigrade. So just for a little bit of fun, I thought we'd see what happens if we take some liquid nitrogen at minus 196 degrees centigrade and pour it into some pretty much boiling water. Okay, and this is what happens. There's no real point to that, it was just for fun, you understand. Okay, so this liquid nitrogen is extremely cold, and we can use it to cool down oxygen gas so that it too becomes a liquid. And that's what Chris has been doing over here. So this cylinder contains oxygen gas, and Chris has been passing the oxygen gas through a coil of copper that sat inside some liquid nitrogen. And the oxygen has been turning into a liquid itself. And so this vacuum flask contains liquid oxygen. And I just want to show you one interesting thing about liquid oxygen. I'm going to pour it into this test tube. And you may be able to see that although the air contains 1/5 oxygen, and the air of course is completely transparent, and yet oxygen, when it becomes a liquid, turns this lovely blue colour. Okay, so we're going to use this liquid oxygen then to fill this flask with oxygen. So I'm going to pour this in, and we'll add a bit more for good measure. That should be enough. Okay, and so the oxygen, the liquid oxygen, is warming up as it touches the flask, and it's evaporating and it's turning into oxygen gas. And as it turns into gas, it's pushing the air. You can see the fumes coming out the top here. It's pushing the air out of the flask and filling the flask with oxygen. And just to help that along a bit, I'm just going to swirl this around. Okay, you can see a little bit of liquid oxygen there, that lovely blue colour sloshing around in the bottom of this flask. So that's gradually evaporating, and that's filling the flask with pure oxygen. Of course, we could have just taken a hose from this cylinder into the flask and filled it with oxygen that way, but I think this was more fun. Okay, while that last little bit is evaporating, the next thing we're going to do is to get some phosphorus. There are two kinds of phosphorus, red phosphorus and white phosphorus. This is white phosphorus, it's the more reactive kind. It's so reactive that it actually reacts with the air. If you just leave it sitting on a bench, it will actually catch fire after a few minutes, and so we store it under water. So I'm going to fetch out this piece of white phosphorus, and we're going to put it in a little spoon that's suspended from the lid of the flask. Okay, you can see the phosphorus is smoking already as it comes into contact with the air. And that will probably catch fire sometime in the next few minutes, but just to help it along, I'm going to take a glass rod and heat up the end of the rod, and then just touch that against the phosphorus just to get things going. And as soon as the phosphorus ignites, we'll bring down the lights. What you'll see is the reaction of phosphorus burning in pure oxygen. And you can see this lovely white light that's being given out. It's a very vigorous reaction. The flask is filling with oxides of phosphorus. So that's white phosphorus, the bearer of light. Okay, so that's a chemical reaction then which gives out energy in the form of light. I'm going to show you another reaction now which gives out energy again in the form of light, but also in the form of sound. And this is a reaction between a colourless gas, which is in this glass tube, called nitric oxide, and a liquid called carbon disulfide. So this is the carbon disulfide, and we're going to add some of this to the tube, and then we're going to mix them together. So Chris is going to mix the carbon disulfide with the nitric oxide. The carbon disulfide evaporates and turns into a gas. We've got a little bit of water in the tube just to help them mix. And when they're thoroughly mixed, we'll set fire to it. Now this reaction happens reasonably quickly, so we'll just bring the lights down first. So we've seen a couple of reactions there that involve effectively combustion. And combustion can give rise to some very interesting chemistry. And for this, I'm going to set fire to a brand new £50 note as an example of combustion. So let me soak the £50 note in some flammable liquid. And then we'll set it on fire. So this is my £50 note. It's brand new. And there it is on fire. And the flames have gone out. But the £50 note, I'm pleased to say, is entirely intact. I'm very pleased about that. Now, the reason that the £50 note survived has to do with the choice of liquid. So this liquid was 50% alcohol, which is inflammable, and 50% water. And it was the water that protected the £50 note. It absorbed heat and it stopped the note from burning. So really that's not too surprising, because we know that we use water to put out fires. The fire brigade carry water with them, they have hoses, they use water for fire extinguishing. So let's have a look at some different ways of putting out fires. And I've got here 3 fire extinguishers based on different kinds of chemistry. Now it would be very surprising, wouldn't it, if we could use a fire extinguisher not to put out a fire, but to make a fire worse. It would be really surprising if we could use a fire extinguisher to start a fire. Okay, let's look at the first kind of fire extinguisher. So this is called a water fire extinguisher. It contains water under pressure. When you let the extinguisher off, the water comes out of the hose, you soak the fire, and you put the fire out. Now, if I let that off in here, it would just flood the lecture theatre. So we'll do something else that's equivalent from the point of view of chemistry, and that's to use a water pistol. So this water pistol contains just ordinary tap water. I can pressurise it, and we can... Be careful what you wish for. So this is just like that water fire extinguisher. It squirts a jet of water. So could we use this to start a fire? Well, for this I'd like a volunteer, please. Who would like to volunteer? You were very quick. Let's have a hand for our volunteer, please. And what's your name?
Kiara.
Kiara. Right, Kiara, if you'd like to put on these safety goggles. They're special safety goggles because they're tinted. They're nice trendy shades. All right. And what you're going to do is to squirt the water pistol at a little metal dish. Can you see that on the little stand there? And that dish contains a mixture of silver nitrate and finely powdered magnesium. And if you can get a little bit of water to land on it, we'll see if that can start a fire. Now, because this contains magnesium, it's going to produce a very bright light. So my suggestion and my recommendation is that you don't look directly at the dish, but instead you look to one side. Now, you do need to look at the dish because you need to see if you can hit it with the water, so that's why we've given you these special goggles. All right, so off you go. See if you can get a bit of water into that dish. Oh, well done. Thank you very much. Okay, thank you. Okay, so that was the first kind of fire extinguisher. That's the water-based fire extinguisher. So if you see a little fire involving magnesium and silver nitrate, don't try to put it out with that. This is the next kind of fire extinguisher. It's called a carbon dioxide fire extinguisher, and it contains liquid carbon dioxide under very high pressure. So I'll just pull out the pin and point the nozzle up, and we'll just set this off. Okay, so as you can see, the liquid carbon dioxide under very high pressure comes out through the nozzle and it turns into a gas. Now, carbon dioxide is often one of the main results of combustion. If something like wood or paper is burning, the carbon reacts with the oxygen in the air to produce carbon dioxide. So the carbon dioxide is the end product of combustion, and that's why it's good for putting out fires. So we use the carbon dioxide fire extinguisher to smother a fire, to exclude the air and therefore exclude the oxygen, and then the fire goes out. So it'd be a bit odd if using a fire extinguisher like this would actually make the fire worse rather than better. Well, let's see what that might look like. So again, we're going to use carbon dioxide in a very concentrated form, in the form of solid carbon dioxide or dry ice, which is something that we saw a little bit earlier in the lecture. So this is a block of dry ice, and again we're going to use magnesium. So I have some magnesium metal here, and I'm just going to make a little pile in a little trough that we've cut inside the block. And I'm going to set fire to the magnesium, and once it's on fire, Chris is going to put the other half of the block on top, and then the magnesium will be sort of trapped inside. And if we bring the lights down, and you can see the combustion is becoming more vigorous. And this is magnesium burning in carbon dioxide. So it's not putting the fire out, it's actually supporting combustion. It's giving off this beautiful light. The white smoke you see is magnesium oxide. This is the sort of stuff that's used in indigestion tablets, that kind of thing. I wouldn't recommend that for dealing with indigestion. So the magnesium combines with the carbon dioxide to make magnesium oxide and carbon. Thank you. Okay, we have a third kind of fire extinguisher, and that's this one. This is called a dry powder fire extinguisher. It contains a powder and it's pressurized. When we set this off, the powder comes out of the hose and we can squirt it at the fire and put the fire out. Now, these are actually extremely good fire extinguishers. If you have an extinguisher in your kitchen or one in your car, it's probably a dry powder extinguisher. And these extinguishers usually contain something like sodium or potassium carbonate or sodium or potassium bicarbonate. They're very effective extinguishers. They're good for dealing with all kinds of fire, and it would be very surprising if using the powder out of one of those could actually make combustion faster or make it worse. Well, perhaps it can. In this spoon, we have a gram of commercial gunpowder. It's made from a mixture of 3 ingredients. Saltpeter, whose chemical name is potassium nitrate, and that acts as a source of concentrated oxygen. We call that an oxidizer. It contains charcoal, which acts as the fuel, and that burns in the oxygen released by the potassium nitrate. And it contains sulfur, and the sulfur is there to aid combustion to make the gunpowder burn more easily. What would happen if we took gunpowder and instead of using charcoal, which is the main fuel, we use some of the powder from a fire extinguisher? So this seems pretty odd. We're going to take away the main fuel from the gunpowder and we're going to replace it with something that's used in a fire extinguisher. In fact, we're going to use potassium carbonate for this. So if we mix those 3 things together, that is potassium nitrate, potassium carbonate and sulfur, we get something called yellow powder. And so in this spoon we have a gram of black powder, and in this spoon we have a gram of yellow powder. Now, what we're going to do is to heat up these 2 spoons, and we'll see if there's a difference between these 2 powders. So there's the gunpowder, and this is the yellow powder. Now, gunpowder, when it burns in the open, doesn't make a bang. It just burns with a puff and a little cloud of smoke. So we're not expecting the gunpowder to make a bang. The yellow powder, however, very probably will make a bang, and it could be fairly loud. So sometime in the next minute or so, there could be quite a loud bang, and you might wish to cover your ears for this. Now, as the spoons heat up, at some point the gunpowder will get hot enough that it will ignite, and we'll see a puff of smoke. The yellow powder is a little bit different. Inside that spoon, the materials are starting to melt, they're flowing together, and some chemistry is taking place. The chemical composition is actually changing as a result of being warmed up. And at some point, that new mixture of chemicals should give rise to a little explosion. So it looks as if the gun... and a beautiful smoke ring. Okay, so that's some of the science of combustion, and that's how the powder from a dry powder fire extinguisher could actually make combustion a little bit worse. So if you remember, one of the questions that we're asking in this lecture is whether a chemical reaction can go backwards. And I said this is a very interesting question. Well, let me show you a fascinating reaction. So in this beaker is a colourless liquid. I'm going to add a second colourless liquid. It remains colourless. I'm going to add some yellow liquid, and it turns orange. I'm going to add a little bit of red liquid, and it goes sort of green colour, kind of muddy colour. Now, in a minute or so, that muddiness will fade away, and we'll be able to see the colour of the solution. And what I want you to do is to watch the colour of this solution as it changes. Now, there's a rather interesting story behind this reaction. It was first discovered in about 1951 by a Russian chemist called Boris Belousov. And he was trying to study the way citric acid behaves in the human body. And so he was mixing various materials together in a beaker, and he discovered some very interesting colour changes, and in particular he discovered an oscillating chemical reaction. That is, a chemical reaction that went through a sequence of colour changes and then came back to the starting point. So you can see that muddy colour is fading, and we've got a green solution, and the solution is now gradually turning blue. So remember that it started out green and it's turned blue. Now Belousov he was very excited by the idea of an oscillating chemical reaction, but that's sort of like a reaction that goes backwards. And people thought that reactions didn't do that sort of thing. So he wrote this up and he sent it off to the top chemistry journal in Russia, and the editors looked at this and they rejected the paper because they said that couldn't happen. Okay, it's now turned from blue to red. So it went green, blue, red. So Belousov had his paper rejected, and so he sent it to another journal, and they did the same thing. They rejected it as well, because they thought chemical reactions just shouldn't behave like this. There must be something wrong. So he got pretty depressed about this. In fact, he got so depressed, he actually gave up being a scientist, and his discovery was sort of forgotten. And then about 10 years later, a student of chemistry, Anatol Zhabotinsky, a Russian student, discovered Belousov's notes. That's turned back to blue. That's turned green. All right. So remember that sequence. We were green for a little while, then blue, then it went red, then back to blue briefly, now it's green. So Zhabotinsky discovered Belousov's notes, and he recreated this experiment, and he was able to get this published at a conference in Vienna, and then the whole world knew about it, and it became quite a sensation. And people got very excited about these kinds of reactions. So you can see it's gone back to blue, it's now turning back to red, and it will keep going through that sequence of colours. So it seems as if we have a reaction that sort of goes backwards, or at least it goes round in a cycle. So lots of people started to study these reactions, and they came up with other kinds of oscillating reactions. But I want to show you one that has quite a nice story to it, because this was discovered not by professional chemists, but by a couple of school teachers. And their names were Briggs and Rauscher, and they were working in a high school in San Francisco, and they were using the school chemistry labs after hours, and they discovered a different kind of oscillating reaction. So again, I have a clear liquid, I add a second clear liquid, and a third clear liquid, and it turns amber, We'll keep watching. It turns blue, very dark blue. So that's a little bit like the clock reaction. It's the same thing, it's the reaction between starch and iodine. But this time, it doesn't stay blue, it's going clear again. So it's become clear, now it's going back to amber, and if we keep watching, back to blue again. Okay, so those are two oscillating chemical reactions. So it seems as if we've found a chemical reaction that does actually go backwards. But really that isn't what's happening. It's not like a ball rolling downhill and then changing its mind and rolling back uphill again. It's more like a ball going down a sort of a helix. It gets back to the same colour as when it started, but it's not really in the same condition because some of the chemicals have been used up. And we can watch these oscillations happening, but after 10 or 20 minutes, they will come to a stop. And that's because the chemicals have been used up. So we haven't really found a reaction yet that can go backwards. So does that mean that our theory of chemical reactions is correct? Remember, our theory is that chemical reactions are like a ball rolling downhill. The chemicals go from high energy to low energy, and they give out that energy difference in the form of heat or light or sound or whatever. Well, let's look at this reaction. This is a reaction between two powders. So in this beaker is some barium hydroxide. It's a white powder. I've got a block of wood. I'm just going to put some water on the surface of the wood to make a sort of puddle. And I'm going to stand the beaker in the puddle. And then in this beaker, in this flask, I have some ammonium chloride. So I'm going to add the ammonium chloride to the barium hydroxide. And I'm going to stir it using this probe, which is attached to this thermometer, this digital thermometer. So you can see the temperature there is about 20 degrees. But let me start to mix the powders together, and we'll see what happens to the temperature. So the temperature's falling very quickly, well below 10 degrees now. And the temperature's just gone negative. This is now below 0 degrees. So it's minus 7 degrees. So the temperature is falling very rapidly. The other thing that's happened is that it's turned from a solid into a liquid. So it's now become a sort of slushy white liquid. The temperature is down at minus 15 degrees, so well below the freezing point of water. Now remember, I stood it in a little puddle of water, so what should have happened is that water should have frozen, and there we are, it's frozen it to the block of wood. So that's pretty strange, because that's a reaction that didn't give out energy, it's a reaction that took in energy. It actually took in heat from the surroundings, and that's why the surroundings, such as the thermometer, dropped in temperature. So that's a bit like putting a ball on a slope and seeing the ball roll uphill. Right? It shouldn't happen. So this is a very strange reaction, and it means that our theory of why chemical reactions happen isn't quite right, or at least it isn't complete. There's something else that's missing. So what's missing in our theory of how chemistry happens? Well, I'm going to illustrate this with a little computer game. What we've got here are 100 disks, and each disk is yellow on one side and it's red on the other. And the bar down the right-hand side shows you the proportion of disks which are yellow. And I've started them all off as yellow, and let's see what happens when we run the little simulation. So about 100 times a second, the computer is choosing a disk and it's deciding either to keep it the same colour or to flip it over. And you can see on the right-hand side the proportion of red and yellow. Now we started off with all the disks yellow, and very quickly we've got to a state where about half of them are red and about half of them are yellow. Let's try it again. This time we can set them all to red. And again we'll run the little simulation. So they start off all red, but very quickly they come to a state where about half of them are red and about half of them are yellow. So I want me to say this is to think that we started the disks off in a very ordered state. They were all the same colour. And as the simulation ran, the level of disorder increased. Okay, it went from an ordered state to a more random state. And this is such an important idea, we give it a special name. We call the degree of disorder entropy. and we say that entropy tends to increase with time. We started off with things very ordered, and they became very disordered. And the reason this happens is very simple. It's because there's only one way for the disk to be all yellow, but there are lots and lots and lots of ways for the disk to be sort of roughly half yellow and half red. And so it's just simply counting the number of different ways of arranging these disks that causes the disk to go from an ordered state to a disordered state. Now you might think, well, hang on a moment. If we wait long enough, sooner or later, by chance, all of the disks will become yellow again. So the system would then have gone from a disordered state to an ordered state. Now you're absolutely right, but you'd have to wait a long time. This is doing about 100 flips a second. If we did 1 trillion flips a second, you would still have to wait longer than the age of the universe, on average, before you see them all yellow again. So it's almost certain that the world will move from an ordered state to a disordered state. Now I've got a couple of teenage boys, and their bedrooms provide a perfect illustration of this. If I tidy their bedrooms so everything is very ordered and come back the next day, it's almost certain to be in a highly disordered state. And without input from me, it will never go from being disordered to being ordered. So that's the idea of entropy. Entropy increases. And that can drive a chemical reaction. So let's think about a solid. In a solid, the atoms or the molecules are arranged in nice, neat rows. They're very ordered in a sort of crystal lattice. In a liquid, the molecules can move around. They're not in fixed positions anymore. So this is a more disordered state than a solid. And a gas is even more disordered because the atoms or the molecules are free to move around. They can fill the container. So as we go from solid to liquid to gas, the entropy or the disorder increases. So there are two things that can drive chemical reactions. There's the ball rolling downhill effect, the decrease in energy, or there is the increase in entropy, the sort of teenager bedroom effect. This reaction is being driven by that increase in entropy. It's gone from a solid to a liquid, and that increase in entropy is so big that it overcomes the fact that it actually has to increase the energy for that reaction to happen. And so that reaction happens spontaneously, and it draws energy in from the environment and cools its environment down. So that's why that reaction happens. So that means that we have two things that can drive chemical reactions. It's not just the ball rolling downhill, it's also the bedroom effect. And so perhaps, now that we have that deeper understanding of chemistry, perhaps we can now find a chemical reaction that goes backwards. Well, to help us find this, I'm going to use the word curious in a different sense. We've used curious to mean strange or surprising or unexpected, but curious can also refer to a desire to learn, so curiosity. And I'm going to tell you a story about curiosity in a young chemist. So his name was Ira Remsen, and as an adult he became very famous. He founded the chemistry department at Johns Hopkins University, and he discovered the first artificial sweetener, that's called saccharin. But as a teenager, he was curious about chemistry, and he used to do some little experiments. And I'm going to tell you a story, in his words, about an experiment which he performed when he was a youngster. Now, the experiment involves the reaction between copper and nitric acid. And so when we get to the appropriate point in the story, I'm actually going to show you the reaction. And the reaction is going to happen in this flask. In this cylinder at the top, we have some nitric acid, and in the flask we have copper. Now the copper, for reasons you'll see in a moment, is in the form of a coin. Now we can't use a modern penny or two-penny piece because they're actually made of steel with just a thin coating of copper. So I've got an old-fashioned penny here. This was made in 1945. So this is actually made of solid copper. So we put one of these pennies into the flask, and we're going to do this reaction in a sealed environment, in a sealed flask. Any fumes that are produced will be led away through this tube and absorbed in this sodium hydroxide, for reasons that will become apparent in a moment. Okay, so this is the story of Ira Remsen. While reading a textbook of chemistry, I came across the statement, nitric acid acts upon copper. I was getting tired of reading such absurd stuff, and I determined to see what this meant. Copper was more or less familiar to me, for copper scents were then in use. I'd seen a bottle marked nitric acid on a table in the doctor's office where I was then doing time. I did not know its peculiarities, but I was getting on and likely to learn. The spirit of adventure was upon me. Having nitric acid and copper, I had only to learn what the words act upon meant. Then the statement, nitric acid acts upon copper, would be something more than mere words. All was still. In the interest of knowledge, I was even willing to sacrifice one of the few copper cents then in my possession. I put one of them on the table, opened the bottle marked nitric acid, poured some of the liquid on the copper, and prepared to make an observation. So let's add the nitric acid to the copper and see what happens. I think you can see that quite a vigorous reaction is taking place. We've got some sort of green liquid, it's bubbling away, some fumes are coming off. All right, let's continue with the story. But what was this wonderful thing which I beheld? The scent was already changed, and it was no small change either. A greenish-blue liquid foamed and fumed over the scent and over the table. The air in the neighbourhood of the performance became coloured dark red. A great cloud arose. This was disagreeable and suffocating. How should I stop this? I tried to get rid of the objectionable mess by picking it up and throwing it out of the window, which I had meanwhile opened. I learned another fact. Nitric acid not only acts upon copper, but it acts upon fingers. The pain led to another unpremeditated experiment. I drew my fingers across my trousers and another fact was discovered. Nitric acid acts upon trousers. Taking everything into consideration, that was probably the most impressive experiment and, relatively, probably the most costly experiment I have ever performed. I tell of it even now with interest. It was a revelation to me. It resulted in a desire on my part to learn more about that remarkable kind of action. Plainly, the only way to learn about it was to see its results, to experiment, to work in a laboratory. So that's the reaction of nitric acid with copper, and it's produced these dark brown fumes, which you can see, and those fumes are called nitrogen dioxide, and they are actually pretty unpleasant, which is why we're doing this in a sealed apparatus. But nitrogen dioxide is a material that can help us understand this question about whether a chemical reaction can go backwards. So in these tubes, we have equal amounts of nitrogen dioxide. And what I'm going to do is to take one of the tubes and to place it in iced water so that it will cool down. And the other tube I'm going to place in hot water to heat it up. So we'll come back in a moment and see if they're changed in any way. So let's have a little look at the chemistry that's going on inside those tubes. Now, nitrogen dioxide has a molecule which consists of one atom of nitrogen and two atoms of oxygen. If we have two molecules of nitrogen dioxide, they can react together to form one molecule of another oxide of nitrogen called dinitrogen tetraoxide. Now that process releases energy. When that extra nitrogen-nitrogen bond is formed, it gives out energy. So that's like the ball rolling downhill. The ball rolling downhill wants the nitrogen dioxide to come together and form dinitrogen tetraoxide. But the dinitrogen tetraoxide can split up. The molecule can split in half to give two molecules of nitrogen dioxide. And because for every molecule of dinitrogen tetroxide we get two molecules of nitrogen dioxide, we have twice as many molecules. They can be arranged in many more ways, and that means the entropy has increased. So the entropy tends to drive this reaction from the right to the left. So these two effects, the ball rolling downhill effect and the teenager bedroom effect, are driving this reaction in sort of opposite directions. What happens is that the reaction actually goes in both directions at the same time. And it reaches a sort of balance. We call it an equilibrium, where there is some nitrogen dioxide present and some dinitrogen tetroxide present. And the relative proportions of these depends upon the temperature. So if we increase the temperature, we put energy into the system. That's like pushing the ball uphill, and we go from right to left. And if we cool the system down, then conversely we go from left to right. So that's the prediction. And we can test the prediction because nitrogen dioxide is this dark brown gas that you see in the flask here, but dinitrogen tetraoxide is colourless. So if we go back to our tubes, this is the tube that was in the cold water, and you can see that it's become a paler colour, and this is the tube that was in the hot water. So I just put these side by side. You can see that heating up this gas has made it darker brown, contains more nitrogen dioxide, whereas cooling it down has made it less dark, it contains more dinitrogen tetraoxide. And just to check our theory, what we can do is we can take the hot tube, the dark tube, and place it into the cold water. And then the cold tube, which is the paler colour, we can place that into hot water. And we'll come back and have a look at those in a moment, and we'll see if they've swapped places. Okay, so that really brings us towards the end of the lecture. What I want to do is just to show you one more curiosity, and it concerns a rather interesting and unusual element. Now, this element was discovered in a mine outside a little town called Ytterby, which is near Stockholm in Sweden. And they had been extracting minerals from the mine, and they found a mineral that seemed rather peculiar. They couldn't understand what it contained until they realised that it contained a new element. This was sort of the beginning of the 18th century. Now, in those days, if you discovered a new element, you got to choose its name. And they decided to name the element after the town of Ytterby. So this element is called yttrium. What's rather interesting is that this mineral contained not just one new element, but they found out it contained 4 new elements. And so they decided to name all 4 elements after the town of Ytterby. So these 4 elements are called yttrium, ytterbium, erbium, and terbium, which is a little bit confusing, I think. We're going to look at the first of these, yttrium. Now, yttrium can be used to make a compound, and I have some of the compound here. It's called yttrium barium copper oxide, and it's just a hard black lump of ceramic material. What I'm going to do is to put it into some liquid nitrogen. And so that yttrium barium copper oxide is now being cooled down to minus 196 degrees. That takes a moment or two to cool down. So while we're waiting, I also have in this cup another piece of identical material, exactly the same as the first, and I'm going to cover this in liquid nitrogen. So that too can be cooling down. Now, at room temperature, this material isn't very remarkable, but when it gets sufficiently cold, it has a very interesting and very strange property. It becomes what we call a superconductor. Now, a superconductor is a material that has lost all its electrical resistance. A material which has 0 electrical resistance has the property that it can repel a magnetic field. So this ring is a ring made of steel, and it's covered in little magnets, very strong magnets. They alternate North Pole, South Pole, North Pole, and so on. And in a minute, when this is cooled down, we're going to see if that yttrium barium copper oxide can repel the magnetic field produced by these magnets. This just takes a moment or two to cool down. So if I look in here, I can see they're boiling away very vigorously. That means the ceramic material is giving up its heat to the liquid nitrogen, is boiling the liquid nitrogen away and cooling down in the process. So essentially, I'm just waiting for the boiling to stop. When it stops boiling, that means the ceramic material has reached the same temperature as the liquid nitrogen. So it will then be at minus 196 degrees. Okay, so let's fetch this out then, and let's see if this can repel magnetic field. Okay, So this is actually quite a special kind of superconductor. It's what we call a type 2 superconductor. And that means that as well as repelling magnetic field, it can also trap magnetic field. Now remember, I've got another one of these sitting inside this polystyrene cup, and underneath is a cylinder, and on the top of the cylinder is a very strong magnet. Now the field from that magnet was already passing through the ceramic material before I added the liquid nitrogen. So I've now cooled it down. It should have become a superconductor, and hopefully it will have trapped that magnetic field. So it should still be gripping onto that field. That means I should be able to take away the support from this cylinder. And by the way, on the outside of the cylinder, we've put the logo for the International Year of Chemistry. 2011 has been a year-long celebration around the world of the delights of chemistry and of the importance of chemistry for our everyday lives, and I thought it would be a nice way to just mark that occasion. So I think this has cooled down now, so I'm going to see if I can lower this very carefully. Okay, well, thank you very much. That pretty much brings us to the end of the lecture. Just before we wrap up, I thought we would finish with a rather nice demo. But just before we do, I just want to ask you to join me in thanking somebody who's put a lot of effort into helping me prepare and deliver this lecture, and that's Chris Brackstone. Okay, just before we finish, I thought we'd take a look at this block of dry ice. If you remember, we burned some magnesium inside this block of dry ice. So the chemistry here was that the magnesium reacted with carbon dioxide to produce magnesium oxide and carbon. And if we look at the surface of this, we can see that it's coated in a white powder, and that's the magnesium oxide. And if we dig down inside, the black powder is the carbon. And then finally, we swapped those two tubes over. We put the dark tube inside the iced water, and we put the light-coloured tube in the hot water, and we can see they have indeed swapped places. So the tube that was dark has been cooled down, has become light, and the light-coloured tube has been heated up, and it's become dark. So we have the rather curious conclusion that chemical reactions can go forwards and backwards at the same time. All right, well, that really is the end of the lecture, but I thought we'd have just one more demonstration to finish. And I thought what we would do is to repeat one of the earlier demonstrations. It's the demonstration of the reaction between nitric oxide and carbon disulfide, but I thought we'd do it on a slightly bigger scale. Right. So Chris is bringing on a tube of nitric oxide. So I'm going to add the carbon disulfide. And again, Chris is going to mix these together. And once they're thoroughly mixed, we'll set fire to the end of the tube. All right, and we'll put the lights down for this. I'd just like to say thank you all for coming. Here we go.